Question number 22, a basic question right here. And let's see, it says a liquid of density rho is coming out of a hose pipe of radius A with horizontal speed V. So the question is essentially related to the momentum and the change in momentum, and you calculate the force. It hits a mesh, 50% of the liquid passes through the mesh unaffected. That means whatever was the speed before hitting the mesh, after passing the mesh, the speed is same. 25% loses all of its momentum, and rest 25% bounce with the same speed. And we need to calculate the resultant pressure. Well, the pressure is created by the force, and force is exerted whenever there is a change in momentum. In other words, the first 50% which went unaffected is not going to exert any force. Now let's talk of the 25%. Now here, let me straightway go with the calculation. For the 25%, say, you can go in this way. Rho AV is the mass of the liquid coming per unit time, that is originally coming from the pipe, divided by 4. So that's a 25%. It loses all of its momentum, so the change in velocity will be V. So that's the force which is exerted by the 25% part which lost all of its momentum. And the next is the 25%, so that would be rho AV by 4, where A is the cross-sectional area, do not mind. And this one rebounds with the same speed, so the change is going to be 2V. So this plus this will be the force, which is 3/4 and per unit area. So quite obviously, it's straightforward. Option number 1 would be the correct option for question number 22. Shall we move on for question number 23? Yes, please. Question number 23, another topic from experimental physics, and it has been set from the concept of meter bridge. By now, you must have very properly realized that the topics related to experiment is of immense importance when it comes to JEE Main. And mark my word, these topics are very much important with regard to JEE Advanced as well. As of now, let's see the question, and it says the resistance of the meter bridge AB in the given figure is 4 ohm. So let me just show you where is the meter bridge. So there is a meter bridge AB, and the resistance of the meter bridge is 4 ohm. So here the resistance of the meter bridge, so here our AB is 4 ohm, and since it is meter bridge, so resistance per unit length would be 4 ohm per meter. That's very straightforward. With a cell of EMF 0.5 volt and a rheostat resistance 2 ohm. So here let me write, when EMF is 0.5 volt, so here it's given, and a rheostat, let me show it in the figure. First, let me pick up all the data of 2 ohm. The null point is obtained at some point J. When this cell is replaced by another one of EMF E2, so there is another cell now next time, E has been replaced by E2, the same null point, notice the word, same null point J is found for RH equals to 6 ohm. And on the basis of this data, we need to calculate EMF E2. So the idea is, say, let's try to see the figure, then I'll help you conclude. So here is the situation. You see that RAB, that's 4 ohm, and as I've already said, the resistance per unit length to be 4 ohm per meter as well. When this is 0.5 volt, the resistance, this is 2 ohm, there is a certain balance length. And when this changes to E2, the same balance length would be obtained, right, when the new rheostat value comes out to be 6 ohm. So this is a simple concept of balancing. And so here let me write the first equation, that's going to be 0.5 volt, whatever would be here, the same value would be there. So that's 6. Let me say that this length is x, where the balancing comes out. So that will be 4 multiplied by x, because this is resistance per unit length as well. And that's 4 plus 2, that's 6. That's the first case, that this is 4, this is 2. So in the first case, 4 plus 2, that's happening to be 6. All right, and in the second situation, let's try to understand. When this is replaced by E2, all right, but this remains as 6 itself, and the balancing length is same. So that will be 6 multiplied by, you could see, 4 into x. That's fine, all right, because you could see that this is 6 and the balancing length is same, which is x. So resistance per unit length, that's all straightforward. And 4 plus 6, that will be 10. So in the second case, the total resistance is going to be 4 plus 6, 10. Okay, so here are two equations and you can easily solve for two unknowns. And what I'll get is that the value of E2 when you solve, it's so straightforward. That's going to be option number 3, which stands out to be the correct option. Now it's time to move to the next question. There we go now for question number 24. And the question is something like this. A body of mass 1 kg falls freely from a height of 100 meter on a platform of mass 3 kg. Let me try to depict it with the help of figure as well. I think that will be a better way to go. So here is a platform and the platform has a mass of 3 kg. And this is being mounted on top of a spring, and the spring has a spring constant K, and you could see that the spring constant is quite huge. The body sticks to the platform and the spring's maximum compression is found to be X. We need to calculate the maximum compression. What we'll do is say, here is the 1 kg particle, and this 1 kg particle is being dropped from a height of 100 meter. And let me calculate the speed of the 1 kg particle just before the collision. So when I go for the instant just before the collision, that's going to be under root of 2g and height, which is 100. So this is the value of speed of 1 kg particle just before the collision. And immediately after the collision, if we would like to calculate the speed, one can use linear momentum conservation, and so easily what I can calculate is V is the speed of the combo blocks immediately after the collision, and that is going to be V0 by 4. That's straight away from linear momentum conservation. 1 into V0 is 4 into V. So you get the value of speed just after the collision. One more important thing at this case is you also need to consider the fact that initially the spring was compressed because of the mass of the platform. However, if you would want to calculate that, the initial compression x0 will be 3g divided by k, and this can fairly be neglected owing to the value spring constant is 10 raised to the power 6. And this is 30, so the value would be very, very, very small, and you can fairly neglect with tolerable error. So I am into the assumption now, initially the spring is not compressed. So here, once you calculate the speed of the combo just after the collision, what I can write is half, the mass is 4, into V square is the kinetic energy immediately after the collision, and that will completely turn into the elastic potential energy, half k x max square. And when we solve this thing, the calculation of xm comes out to be 2 centimeter. And unfortunately, 2 centimeter is the option that we have nowhere. So we maintain the stand that there is no option correct, or very closely correct option is also missing. So in that case, we reserve our answer to be 2 centimeter, and therefore say that there is no option which matches the solution that we have found. Fair enough. Now it's time to go to the next question.